Welcome to this video titled Moment of Inertia, the fundamental theorem of calculus at its finest. There will be lots of problem solved. This is video 5 in my rotational motion playlist. Before diving into the moment of inertia, let's talk about the fundamental theorem of calculus and how to interpret the definite integral in physics. This symbol on the left represents a definite integral. When you see this integral symbol with bounds at top and bottom, think of it as a sum. It's adding up infinitely many tiny contributions. The dx on the right stands for a very small number, sometimes called an infinitesimal. It's helpful to think of it as a finite number, like 0.001, although it's much smaller than that. The smaller dx gets, the more accurate the sum becomes. Once it's small enough, making it smaller doesn't change the result. That's the power of the definite integral. The definite integral of f of x dx is equal to this sum. You take the function and you evaluate at the bottom bound a, and then you multiply that function by dx, a small number. Then you add it to the function evaluated at a plus dx, and you multiply that by a small number. And then you add it to the function of a plus 2 dx, and you multiply that by dx. And you keep adding terms until you get to f of b minus dx. Multiplied by dx. In physics, a definite integral should always be thought of as a sum like this, where each term has a physical meaning. For the function x cubed plus 2x, write the sum that this definite integral is equal to. The lower bound a is 2, the upper bound b is 4. First we evaluate f of 2, that's 2 cubed plus 2 times 2 multiplied by dx. Then you increment by dx to get the next term. Now it's going to be 2 plus dx cubed plus 2 times 2 plus dx. That whole thing multiplied by dx. And then you keep adding terms until you get to 4 minus dx cubed plus 2 times 4 minus dx, that term multiplied by dx. Here's a definite integral between 1 and 5 for the function 4x cubed. This integral represents a sum of an astronomical number of tiny terms. If we set dx equal to 10 to the negative 7, we'd be adding up a billion separate terms. Doing that by hand would take multiple lifetimes, and even a computer would struggle with the sheer size of the calculation. But thanks to the fundamental theorem of calculus, we can compute this massive sum in a matter of minutes. The procedure is to find a function whose derivative gives the original expression and evaluate it at just 2 endpoints. To compute this sum quickly using the fundamental theorem of calculus. First, we must find a function whose derivative is 4x cubed. That function is x to the 4th, and then we evaluate it between 1 and 5, which is 5 to the 4th minus 1 to the 4th equals 624. In this example, we computed the exact value of the entire sum, 624, in mere seconds. It's one of the most beautiful and useful ideas in all of physics and mathematics. Thank you, Isaac Newton. On this slide, I'll explain what moment of inertia is and why it plays a crucial role in rotational motion. Then I'll walk through examples where the fundamental theorem of calculus helps us compute it for various shapes. Picture a solid sphere spinning gracefully about an axis through its center. It's made of countless tiny mass elements, dm, all spinning together in harmony. You can break the sphere down into many small mass elements, many small units of volume that have mass, where if you add them all together, they equal the entire sphere. If we want to compute the kinetic energy of the sphere, the way to do it is to sum the kinetic energy of each one of the mass elements. Kinetic energy is equal to 1/2 mv squared, where mi is the ith mass element and vi is the velocity corresponding to that mass element. But we know that v is equal to omega times r. Each one of the particles on this sphere or any spinning object has the same angular velocity. Because the omega is the same for every particle, this is the expression for kinetic energy of a rotating object, also known as rotational kinetic energy. And the term in parentheses, the sum mi ri squared, is what is known as the moment of inertia. And the moment of inertia describes how mass is distributed around a rotation axis and determines how much an object resists change in rotational motion. In the discrete form, I is equal to the sum of mi ri squared, and for a continuous body, I is equal to the integral of r squared dm. Here we have a basic moment of inertia calculation. Two masses, m1 and m2, are connected by a rigid massless rod of length L, as shown in the diagram. Find the moment of inertia I about an axis perpendicular to the rod and passing through the green dashed line. Express your answer in terms of m1, m2, x1, and x2. Here's mass m1, which is a distance x1 from the axis of rotation, and this is mass m2, and this is a distance x2 from the rotation axis. Well, we know that I is equal to the sum of mi ri squared. The moment of inertia is equal to m1, the mass of this object, times x1 squared, where x1 is the distance m1 is away from the rotation axis. And then you add that to m2, multiplied by x2 squared. Now let's look at an example where we calculate the moment of inertia for a continuous body. Find the moment of inertia of this rod that has a length of 2 meters and a mass of 5 kilograms. Here's a rod. You can think of it as a metal structure. It's much longer than it is thick or wide. For example, you could think of it as a long nail. You're rotating it about one edge, and the question is, what is the moment of inertia? This is a continuous body, so the way we would analyze something like this is we break this rod up into many small segments. Each one of those segments has a mass, and its mass is given by dm. We're using calculus to analyze this. This symbol, dm right here, what that means is the mass of the individual segment. And dx is the length of the individual segment. dm is equal to lambda times dx, where lambda is a constant. It's the mass per length. In this case, for this problem, lambda would be equal to 5 kilograms divided by 2 meters. So lambda is equal to 5 halves, or 2.5. To calculate the moment of inertia, we take each mass element, we multiply it by the distance it is from the rotation axis squared, and then we sum them all up. And so that's the integral x squared dm. In this particular problem, we integrate it from 0 to 2. So it's the integral from 0 to 2 of x squared lambda dx, because dm is equal to lambda dx. What does this integral mean? Well, this integral is always equal to this sum. So the first term, 0 squared lambda dx, that's looking at the mass element right at the origin. And that doesn't produce any moment of inertia because the radius is equal to 0. And the next one is a distance of dx away from the origin. It's still really close to the origin. You keep summing up the moment of inertias of all these mass elements. In this particular problem, each one of the mass elements has the same mass, but that's not the case in general. And so then you get to this mass element, and you would take dm times this x squared, and you sum all of these up. And if you do that, you would calculate the moment of inertia of this extended object. Well, in order to compute this sum, we use the fundamental theorem of calculus. This is an easy integral to do. The integral of x squared is x cubed over 3. We get lambda times x cubed over 3 evaluated from 0 to 2. And that tells us that the moment of inertia of this object is equal to lambda times 8 over 3. And we said lambda was equal to 2.5. And so that would be 2.5 times 8 over 3.
AcePhysics.org.
Terrific!
Math and physics tutoring with Dr. Hudis.
Here's the next example problem. Find the moment of inertia of the region under the given parabola between x equals 0 and 9 when rotated about the x-axis. Assume a uniform mass density sigma. Sigma is the symbol which represents surface mass density. That's mass divided by area. Imagine this shape is cut out of a metal plate. This question is asking us to find the moment of inertia if this shape is rotated about the x-axis. The problem gives the functional form of this parabola y equals 2 times the square root of x. To solve this problem, we use a standard procedure used in many calculus applications. We divide this shape into many tiny rectangles with width w and height dy. Each horizontal strip is a small rectangle. Its contribution to the moment of inertia depends only on two things: its mass and how far away it is from the rotation axis. This dy is a very tiny number, and when dy is sufficiently small, the strip can be approximated as a rectangle with area dA. The area of a rectangle is width times height. The mass of the strip, denoted dm, is equal to sigma times dA. What this is doing is taking the mass of a given rectangle and multiplying it by y squared, the distance from the x-axis. It's doing that for every rectangle and summing up the billions and billions of terms. That gives the total moment of inertia for the object. dA equals width times dy. The width is equal to 9 minus the x distance to the curve. dm is sigma dA. So the moment of inertia equals the integral from y equals 0 to y equals 6 of y squared dm. We need to write this integral in terms of y only. We know the parabola is given by y equals 2 root x. We can rearrange this to find x equals y squared over 4. So replace this x with y squared over 4. This integral is equal to this infinite sum. This sum is equal to the moment of inertia of this parabola when it's rotated about the x-axis. This is a simple integral to do, and it's equal to 1296 over 5 sigma. And on to the next problem. Consider a triangular region ABC with base B and height h. We wish to find the moment of inertia of the triangle about its base, BC. This length BC is equal to B. Notice the triangle APQ is similar to the triangle ABC. Therefore, the base of this triangle, PQ, divided by the base of this triangle, BC, which is also equal to little b, is equal to the height of this triangle, little h, minus y, and that's the height of the little triangle, divided by the height of the big triangle, which is h.
we'll need to use this ratio to solve the problem. Here's the ratio from the previous page. BC is equal to little b. This line, PQ, is equal to little b divided by h times h minus y. dA is the area of this rectangle, is equal to length times width. The length is PQ, that's this expression, and the width is dy, an infinitesimally small change in the y direction. dm equals sigma dA, the mass of one of these rectangular strips. And so the moment of inertia is equal to the integral from 0 to h of y squared dm. This integral represents this infinite sum, and it's easy to show that the answer is 1/12 sigma bh cubed. Here's the actual work for the integral. It's a very straightforward integral.
Acephysics.org.
Yes! Yes!
Math and physics tutoring with Dr. H.
Oh my!
Acephysics.org.
Good morning, ma'am.
Math and physics tutoring
Dream big.
with Dr. Hudis.